Let's do an example of a linear regression using R. I'm going to use a data set for one particular animal from Rachel Arnold's master's thesis research. We had a litter of red-tailed boas that were born in captivity. And from the very first week of life, she selected 10 of these animals. Actually, I think there were 20 of these animals, and she divided them up into two groups, and 10 animals were fed one diet, and the other 10 were fed a different diet. And then each week she weighed the animals, and she weighed all of the inputs and all of the outputs. So they were kept under a constant temperature regime. And every time the animal molted, she would collect the molted skin and weigh that. Every time they defecated or produced any uric acid crystals, she would weigh that. So she was trying to get all the inputs and all of the outputs so that the data that we're going to look at is data for just one particular animal. So these are the weight of the animal on a particular day, and then what its weight in grams was. So we'll start here then in R. We'll clear the memory, so we'll use the rm command, right? List equals ls. And then I'm going to input the data. I'm going to call the data boa data. So these are boa constrictors. So it's boa data read.csv and then the standard file.choose header t. And then I ask it to display the data. So here we have the list of data. So it does have the header. So this is day in this column, and then weight of the animal in grams in this column. And you can see that on the 26th day of life, the animals weighed this particular animal weighed 71.2 grams. And then on day 391, it weighed 662.7 grams. So it's a nice data set. There are some issues with the data that, not with the quality of the data, but something that we will need to consider a little bit later on. But at any rate, I attached the data set, so attach boa data. And now I ask for a simple plot. Rather than doing box plots here, we will address normality issues and so on in class. But for right now, I just want to look at a scatter diagram to see what it looks like. So I use plot day comma weight, and then I give the x-axis the label of week, and then the y-axis the label of grams. So that's actually incorrect. The label shouldn't be week, it should be days. But at any rate, here is our scatter diagram, and it's not a very pretty graph, but it is labeled, and it does show you what the data look like. I then fix it and change the axis to days, and we can see what that looks like. So let me just click over there. Now I've fixed it, and in addition to that, I've added a line. So the way I add the line is I just use AB line. So this is just a little routine within R, that will allow you to put in a line. It doesn't have to be a regression line, but it is context specific. So in this case, I have AB line and then linear model weight as a function of day. And here I specify that I want the line to be red. Okay, so that gives me this graph over here with this nice best fit regression line, and that is a least squares regression line, just as we described in our lecture last week. So again, it's not a very pretty graph, but it does show you what's going on. What I'd like to do is improve the quality of the graph, something that is more likely to be acceptable for publication. And I'm going to use a package called ggplot2. So the first thing I do is I call up the library, search for ggplot2, and it indicates that it isn't there. So now I need to install that package. And when you want to do that, you can click over here in this window under Packages, and you can search for the package that you'd like to install. And what you will do is you will find ggplot2. There it is right there. So you can check that box and then simply click on the install button here. And that will then take you through this sequence that we have right here. So it's now installing this package. All of these red statements here are comments from the installation routine, and it's quite lengthy, right? It's going through this whole thing here, and it's giving you information that should you need to address some issues with the package, this is your roadmap to how to do that. Okay, so it's rather lengthy, and now it indicates that it's downloaded it, right? So I indicate library ggplot2, and now what I wanted to do is construct a prettier graph. So I ggplot and then boa weights, and then I give this comment right here, and it's incorrect, and that's because I shouldn't be using boa weights. I should be using boa data. So let's try that again. ggplot boa data. So I'm specifying the data set. And then I'm using this command AES. AES stands for aesthetics. And this also is context specific. So I'm indicating that my x-axis is going to be day, my y-axis is going to be weight, and then plus, and then I'm specifying geometric points, right? What the nature of these symbols on the graph should be. And I don't put anything there. So that gives me the default symbols. And when I do that, I get a plot that looks like this. Okay. Now what I can do is I can go through a series of steps here, changing all of that. So I can now try it again with, for my geometric points, I can change the size to size 2 and shape number 23. And I will put on the web page a little document that shows what the various shapes are. But we can scroll through these and we'll look at, we can change the shapes, and we can change the sorts of points that we have. And here, what I've done is I've asked for a line. So that's happening right here. So geometric point size equals 6, shape equals 20. And now, whoops, I've made some errors there. I have a bunch of empty things there. That's what happens when you just copy and paste commands. I believe I fixed that down here. Here we go. So, so geometric ggplot, boa data, the aesthetics, right, plus geometric point size 6, shape equals 20. Plus the geometric smooth method. So here my method is a linear model, and color red and fill with blue. I think I might be one behind. Yeah, there we go. So now what I'm doing is I've done a couple of things here. This red line right here, that's my regression line, my least squares regression line. And you'll notice that there's this blue band around that regression line. So let's zoom in on that a little bit and drag this over to here. That blue band, that is the 95% confidence interval for the regression line. Now, the first thing you'll notice is that the points are not within that 95% confidence interval. That's because the confidence interval here is not for the points. The confidence interval is for the line. Notice that it's wider here on the left-hand side of the x-axis, and it's wider here at the right-hand side of the x-axis. And there's a reason for that. It's narrowest here, right in the middle. Remember what's happening with our regression model. The way we estimate the intercept and the slope of the model. Recall, number one, that the slope of the model is the covariance of x and y divided by the variance of x, and that we know that the line goes through, or rather that the point x bar comma y bar is a solution to the line. So right here in the middle is somewhere as x bar y bar. But x has a 95% confidence interval associated with it, as does y. So there's going to be a 95% confidence interval going in this direction vertically and another one going in this direction horizontally. So my point could be anywhere within that 95% confidence circle. That means that this red line could really be shifted around anywhere in there. Also, when we think about the slope itself is an estimate of the true slope. Remember, we're estimating beta 1 and we're using B1. So B1, that slope, has a 95% confidence interval associated with it too. So if you change the slope, if you anchor the line right here at the center and then change the slope in accordance with that confidence interval, this line is going to either become steeper or shallower. It's going to tilt either up or down depending on where in that 95% confidence interval you are. So then it makes sense that this confidence band actually has this kind of almost hourglass shape, narrow in the center and wider at the extremes. Okay, very good. So now what I want to do, I've got my line there. Now I want to look at what the actual coefficients are. So I'm going to define my new variable called BOA model, and I'm assigning to it the results of this linear model. Weight is a function of day, and I'm using the data set data equals BOA data, and then I ask it to print BOA model. And when I do that, it comes and provides me with this information right here. So my intercept is minus 5.706, which I know can't possibly be true because the animals didn't have negative mass on the day that they were born. And the slope is 1.684. So the first thing you understand, there are two things you understand here. First of all, number one, we really don't care what the intercept is in this example. We're not going to pay any attention to that. And secondly, that perhaps a line isn't the best thing that we should use here. There might be something else going on. And in fact, you know that's true because these points over here are not statistically independent of one another. The weight that an animal has on day 7 is not independent of its weight on day 6, just as your body weight tomorrow is a function to some extent of your weight today. We will address that issue a little bit later on when we start talking about the stock market. All right, so, but here at any rate, there is my intercept and my slope. So that's my estimate of beta 0, and there's my estimate of beta 1. I can ask for a summary, and it now gives me my minimum and maximum values plus the quartiles and the median. And those are for the residuals. So those are the deviations of these points over here from the line. The next thing it does is it provides me with the coefficients. Okay, so my intercept and my slope. It's also giving me the standard error. So here, for example, for the intercept, my estimate is minus 5.7. The standard error is 6.18. Remember what the standard error is. It's the standard deviation of the mean. Now, once I know that standard error, I can use a simple t-test, right, to determine whether that parameter is significant. So, remember all a t-test is simply the estimate divided by the standard error of the estimate. And when I do that here for the intercept, I end up with a p-value which is 0.36. In other words, my intercept is not significantly different from 0. Okay, well, that's good news. The slope here, my estimate right there, the estimated t-value, right, is 63.35, and that turns out to be highly significant, so that I know that my slope for this regression line is non-zero. That's good. Now, what I'd like to do, though, is I'd like to look at what the actual Anova table is. So I'd like to know what the sums of squares are and the mean square and all of that. And I can get that with a command Anova, right there. So there I have Anova, and then parentheses BOA model. Remember, BOA model is what I did up here at the top of this, this console over here. That's the linear model of weight as a function of day. And here it provides me with the Anova table. So I have 1 degree of freedom associated with day. That's the slope. And then I have 50 degrees of freedom associated with the error, and a total of 51 degrees of freedom. Well, there were 52 observations. She did this weekly, so week 1, week 2, week 3, and so on. Okay. So you can see here the sums of squares and the error sum of squares, the mean squares, and then the F value, and it's 4,000 something. So you know that it's going to be highly significant, and in fact it is, right? It is significant at the 0.0001 level, which is not surprising. Now there is one final comment that I would like to make about this, and that is the following. There are two things that we want to look at. One is the R square, that's the coefficient of determination. And in the lecture video, I talk about that a little bit. What is that? That is simply the sums of squares associated with the model here divided by the total sums of squares. So if I take 16991.24 divided by the sum of 169,912.4 plus 21179, I guess there is no decimal point in there. So if I take the sum of the model sum of squares and the residuals, right, the total sum of squares in other words, and divide the model sum of squares by the total sum of squares, I will come up with a value 0.9877. Oftentimes, when you're looking at a table like this, you're also provided something called the adjusted R square. And in this case, the adjusted R square is not quite as good, 9.9874. What is the adjusted R square? The adjusted R square is the mean square divided by the total mean square. Okay, so it's the mean square for the model divided by the total mean square. Why is that different? It's different because in a system in which you have multiple variables here associated with the model, so instead of just day, there might be temperature or something else in there. Sometimes what will happen, especially if, depending on what sorts of sums of squares we use, the results here are going to be somewhat different. The explanatory power is going to change. The sequence of the parameters in the model is going to have an effect. So this adjusted R square is an attempt to take all of that into account. For me personally, most of the time I'm simply looking at the total R, or the R squared here, the 0.9877. So sums of squares associated with the model divided by the total sums of squares. The adjusted R square will become important when we're looking at more complicated models, especially when we're doing multiple regression or stepwise regression. Very good. That's it for today. I will make these data available to you, and then you can run this analysis and include it in your packet of R programs for your records. Very good. See you guys next time.